When using the PV battery configuration tool to design with self-consumption, we typically look at the home's total usage and select a percentage offset. And most of these systems are also AC coupled. So we're going to look at two things here, is AC coupling and self-consumption. So if you're doing an off-grid standalone system, it's recommended that you itemize everything. You go down through all these different rows and columns and set your usage for your various appliances. When we do a self-consumption and we're just offsetting a percentage, usually what we do is we list the kilowatt hours used each month by the customer. So down here we'll go from January to December and list the kilowatt hours used each month of the year. Once we've done that, we let's just drop down a little bit, and so we're not using the top area, so we're going to just sit down at the bottom. We're calculating from main AC loads, not from itemized. If we said itemized, it says I don't see anything above there, so we're not going to do anything. So AC loads, it's looking at this row right here. And then of course we have to input our sun hours, so we go to PV watts or use our Solmetric Sun-Eye or our Solar Pathfinder, determine how many sun hours we have at various locations on the property. Here we have two. One is optimum and the other is southeast roof at 30-degree tilt. So this is the one we're going to be using for this example, and I've selected it right here, number 2. Look at column number 2, irradiance data. Once you've done that, everything else is done for you for the most part. It's looking down here where I've said offset 50%. That's a good safe place to start. And it's also looking at the power conversion efficiency. If you're set up in a bimodal mode, you're going to have one efficiency. If you're going to have a self-consumption, you're going to have another. This is a very, very high conversion efficiency for self-consumption. It may be, I don't know, a little lower than that. Could be down to 74. I'm going to leave it at 78. I see a lot of these self-consumption systems that market at around that conversion efficiency, total round trip. So that being the case, we're going to just go with their standard setting. You'll notice that I have selected over here self-consumption, not bimodal, standalone, or backup. And this, of course, starts off always in formula mode. We're going to design by our formula here. So all these being set, it tells us we need a 7.8 kW PV array if we're going to offset 50% of the energy that the customer is using. So we're using an average. Once we've done that, we can go to the next pages. If we were doing DC coupled, we go to this tab. We're doing an AC coupled system, so we go on ahead and go to the inverter battery design tab. So let's click that. Alright, so in our green cells at the top, we're able to put in some information from our interactive inverter setup. So we have an AC coupled design tool that we would use for this, and you can look at that in a separate video. But all we have to do, let me take out this information that's in here, and I'll show you what's going on. It says we need a 7.8 kW PV array. Well, if you find your module, and let's say it's a 300 watt, it'll tell you need 26 modules to achieve this kW. You say, okay, well, I'm going to take your suggestion and put 26 in, and then it says you're going to need at least a 6.24 kW inverter. Now you have to look at the inverter data sheet. Some of them allow you a larger size ratio of PV to inverter. This is using an 80% capacity. The inverter is rated about 80% of the capacity of the PV array. Well, we don't have a 6.2 model. The next one above that is a 7, so I'm going to go 7,000. And we have one of them, so that's it. So I didn't really design anything. I just sort of took the guidelines that were given to us and, for the most part, came up with the number of modules and the inverter size. Once we've done that, we have the AC coupled system set up. We can drop down and we can select our inverter. There's a lot of inverters out there that you can set up with AC coupling, most of them, but not all of them are set up for self-consumption. So we're going to look at a particular inverter that's designed specifically for self-consumption and AC coupling. This is a Sonnen Eco 20. We have different models here. Let's go up a little bit. We see the smaller models that have a 4 kW inverter inside of them, and then the larger models that have an 8 kW inverter inside. And the when you select this, if you select the 10, it'll identify it as a 10, but the numbers don't change because functionally the only thing that is different inside of it is the kilowatt hour storage, which we're going to look somewhere else for in a moment. So it doesn't matter which one of these, number 10 through the 10 through the 20, they're all going to be the same data here. So it's just a matter of identification. So we've selected that. The tool automatically tells you need one. From the data sheet, from the installation loads tab, it sends over this max load, and it says 6.2 kW is what your inverter has to be rated in order to deliver those loads. It's given approximation because we did not itemize, but it's pretty close to being accurate. So this is rated 8, so we're okay. We only need one inverter. It's a 240 volt AC, so we only need one. We don't need to have two of them to make 240. If you had a 120 volt, then it would give you a suggestion of 2 to get that 240 volt. Alright, so that's done. We're through with the inverter. We have it selected. We drop down and it says battery system design. Now you can input quite a bit right here to affect the size of the battery bank, and I'm going to go down and zero in there. So I zeroed that out just to keep it from showing up. These 4 cells right here, these 4 green cells, you can input and change. The default on them is 80% depth of discharge, a load fraction, 4 days autonomy, the max depth of discharge is 80%, and then we have an average depth of discharge of 20%. Well, with lithium-ion batteries, you can get much deeper into the battery if you want. If you want the average depth of discharge to be, let's say, 60%, you want to really pull energy out of that battery bank, it drops the capacity down. It also drops our autonomy down. So we have lost a lot of our autonomy. In other words, if we have a power outage, we don't have that much stored energy. So if we have cloudy days, consecutive rainy days, we may have a problem. We can get 90% out of this battery, so we could drop that down, and it drops it down a little bit farther. So anyway, I'm going to take this back up. I like to see a little bit of autonomy built into all this. We did change our days of autonomy to 3 from 4 because 3 is a little bit excessive. So anyway, you can leave those blank if you want. What it's going to give you is a really big battery bank, and it's not really necessary. If I take this out and I say lithium-ion batteries, I don't mind having let's just use 50% in this case. Then it'll drop this battery bank size down to 39.5. Now that's for a standalone type of operation. If we're looking at self-consumption, we slide over to the right-hand side, and we see that it's telling us if we want to operate as self-consumption, primarily, not as an off-grid system, but as self-consumption, we only need to have 17.7 kW, or kilowatt hours of energy storage. So that's what we're designing. So we have 2 numbers to look at, and I'm going to pull this 0 back out of here so it'll function and operate. Once we select a battery, we just have to pick one of these, and you have to be sure that you pick a battery that actually goes with your inverter system, especially if they're designed component systems. So we've selected the Sonnen LFP 2.5. That's their new battery, and it tells us we need 8 to achieve this. Now, if I had a larger capacity, you can only go up to 8 with this particular inverter. They're working to change that for the future, but right now we can only have 8. We can only have a 20 kilowatt hour battery bank with their inverter system. So anyway, it works out perfect for us because all we needed was 17.7 right here, and we designed a 20, so we have a little bit of extra margin. Not quite as much as we'd like to have for an off-grid event, but we do have some energy in there. So the line diagram, we would go to the next slide over here. Oh, one more thing to look at. We have this set on a C2 rate. If it's a lithium-ion battery, C2 charge rate is appropriate, and it shows us the max amperage, ampacity, that we can put into this battery based on a C2 charge rate. If we exceed that, we could damage the battery. So we take a look at the inverter. It has a maximum of 125 amps, and the interactive inverter itself has a max capacity of 146 amps. So both of these are less than our max capacity of charging. So we're in good shape. Now let's go to the line diagram page. And here all we're doing is looking at our information. We don't have any DC coupled systems up here. We have an AC coupled. It shows up right there. It says 7.8 AC coupled. And we have the Sonnen battery, and we have the inverter and the battery set up on this line diagram. And we don't really have any circuits on the DC side, so this is left blank. This is all done on an interactive inverter setup. And on this side, what we have is our conductor size. We look at these conductors back and forth from the inverter to the grid and from the inverter to the backup panel. Both of these have 46.1, so that conductor size would be a number 8 minimum. So let's put an 8 on both of those. And then we'd go to the ohms per thousand feet for number 8, and you can look in these tables down here. The little red boxes will indicate which table to look in to find this information. So we looked in table 310 15B16. And blow that up a little bit. So it shows us for our ampacity that we needed a a number 8. The problem is, and it shows that a number 8 in any column. Okay, so number 8 is required, and we have 55 amps in the 90-degree column and 50 amps in the 75-degree column. So then we go to our ohms per thousand feet. We go to table 8. This is actually on the AC side, so what we want to do is go to table 9 for the AC side on this. So let's drop down. These tables are so similar it wouldn't matter which one you selected. Actually, the ohms per thousand feet is almost identical for AC as it is for DC. Alright, let's blow that up just a little bit. And we see for a number 8 stranded, it's 0.78. So we're going to take the 0.78 and put that in here. And I think we've got about 35 feet maximum. And then on this one we have 0.78 and about 30 feet on that one. So our combined voltage drop is 1.4% if the power is being delivered from the grid to the backup panel, to the protected panel. We'd have a total voltage drop of 1.4. If the power is being delivered from the batteries through the inverter to the protected loads panel, then we only have 0.6% voltage drop. So we don't have to size the conductors from the battery. This is all done by the Sonnen battery system design, so we don't have to calculate any of that. You can go through the exercise if you want to, but they put it in the manual and specify what you will use on that. So we look at our performance chart. It shows that we have very poor off-grid capacity. We're looking at our sun hours, our kilowatt hours produced, and then the AC power load and the percentage that we're offsetting. And if we had protected loads, then that would be 50% of our main. But we do produce enough to cover this in certain months of the year, but most of the year we do not. And we can see that down below in our graph. We see our green line is our critical loads, or our protected loads. Blue line is the main loads, so we're at 50% offset with these, and our PV array production does not match the usage production, our usage consumption. And our battery bank is minimal as well. So for an off-grid system, this is marginally functional. We would actually have to go in and calculate what we can actually put into that critical loads panel. It's not going to be 50% of our energy like we designed the system for. It'll be less than that. So how do you do that? How do you back into that? Well, let me show you. Let's go back to our installation loads page. So we have all this set up. If we were to go off grid, I'm going to drop that down to 70%. I know that our conversion efficiency will drop when we're in an off-grid mode, so I'm going to go ahead and put it down to that. I'm going to change this from formula design to actual design, and you see all the red pop up. That's telling us that we do not have the capacity in the battery or in the PV array production to be off-grid in certain months of the year. However, we were looking at 50% of the load offset, and that's not what we're going to do. We're going to go to itemized loads. We don't have any itemized loads listed up here whatsoever. What we have are monthly loads, and we have the actual PV array production that we have from our PV array operating in an off-grid mode. Now we can go up and we can design, and we can start adding loads in, and I'm just going to grab some from another chart here. And let me just grab a few of them. I'll show you how this works. Let's see. Okay, there we have it. So we have put in some loads, and we see what these tally up to, and then we see this drop down. So what it's doing now is subtracting. It's taking what we've added in and pulling it out, and we can keep adding loads until we get into a red zone. When we get into a red zone, we know we've exceeded the capacity, so I'll just keep adding loads until I'm going to add 4 more lines of loads here. Let's see. Alright, we're still in great shape. So we still have plenty of energy, so we can keep on adding until we zero this out. So we have a huge capacity, for off-grid loads, but we are not going to offset 50% of our energy. We're going to select these and adjust it accordingly. Anyway, it's a reverse design process. Typically we start out by identifying all of our loads when we're going for the battery system. But we don't do that as much today. We actually, often build an interactive PV system and later add batteries. And when we do that, we have to go explore in reverse what we can actually set up on it. So anyway, I hope this helped you to understand how this tool works. It's very versatile, and for the most part, it does a lot of the work for you. But you will have to put some information in the green cells in order to get something to activate.